everybody. I am Lisa Miner. I'm representing Multispan, and we're going to continue our series of conversations about GPCRs. Our last conversation was about GPCR assays and what is the best assay for your target. And, and today we're going to talk about orthologues and other things. And I'm joined in this endeavor by Dr. Terry Knacken. Terry, would you like to introduce yourself?
Yes. Hi, folks. I'm Terry Knacken. I'm a pharmacologist at UNC School of Medicine. I've spent most of my career in industry, moving compounds forward from towards candidate status. So my general interests are how do we use medchem and pharmacology to make molecules for therapy.
Thank you very much, Terry. So today, the first thing we're going to do is to talk about, so you found a hit against a GPCR human target. You've done all the stuff that we talked about before. You ran your appropriate screen. You've looked at whether you have activity against the appropriate signaling pathway, and everything looks really good. And you have gotten something that looks relatively potent. You've developed a hit, and you're going to start working on leads. Now, what do you do? What are the next steps to ensure that you're going to have success?
Right. The real question is your molecule that is active in your in vitro human system going to produce the therapeutic activity in humans? You cannot test your compound from the in vitro system in humans. There are safety issues and so forth. So you need some intervening process, and usually that is an animal model. So you might have a compound aimed at human depression. So you will then test it in a rat model of depression. The possible issue here is your compound going to be equiactive in the rat receptor as it was in the human one? Now, in some cases, as shown in the next slide, we have compounds for a compound for NK3. And as you can see from the curves on human and animal species, it is equiactive. So you're in good shape to move forward to at least assume that my compound will produce the same activity in the animal as is seen in my in vitro human system. But how do you predict, will this be true? Well, one way to do this is how similar is the animal receptor to the human? And one scale for doing this is amino acid homology. And so the next slide shows some effects of compounds on the rat versus the human alpha-2 adrenal receptor. There is an 89% homology in terms of amino acid sequence with these two receptors. So you might think, well, this might mean that the receptors are quite similar, and the effects I see in humans will be predictive of the rat. And as you see, there are two compounds here, and that sounds like it's correct. We have compounds that are basically equiactive as inhibitors of the alpha receptor in both receptor species. However, what can possibly happen, and frequently does happen, is shown in the next slide. Inevitably, for example, we've come upon a compound, prazosin, that clearly shows that there is a serious deviation between these receptors. And this poses a question. At one point, will you feel confident that amino acid homology will in fact be predictive of activity in humans and the animal species?
Yeah, you figure here that you've got 89%. what if you take it to 95, 99%? What does that do? I mean, I think you have an example showing that
Yeah.
you can't be sure of that.
Yes, I do. And again, um, this may not happen in all cases, but here we have some data shown from Katie Leach, and she showed that when you do a single acid amino acid mutation of the muscarinic receptor, you make it totally inoperative to acetylcholine, which is a pretty drastic effect. And so that just illustrates this mutation is still a 99.8% homology with the wild type, yet you have complete reversal of activity of the natural transmitter. The next slide shows that this also translates to very severe differences in the affinity of muscarinic inhibitors on this receptor. So this basically shows that very, very small differences in amino acid homology can lead to catastrophic differences in pharmacology.
So your next slide basically shows that you really have to do the testing.
Exactly. Exactly. You can use theory and predictions all you want, but there's never a um, certainty that you will in fact show that the animal receptor effect will be equal to the human receptor effect that you have.
Yeah, that makes things complicated. So you have to have animal model cells, essentially. So I'll talk about that in our third presentation with this, a little bit what multispan has, but you do need to have your animal system and able to be able to compare between human and your animal species, at least to know not to know with a scientific testing method that you actually have molecules that behave similarly before you take it into animals.
Yep.
So, okay, thank you. I
Thank
think
you.
we will take this up again in our next session.